star you to
Fine.
join the room.
Yeah. So I'll let you be the boss. How's that? You can run the show
Sounds
here.
good.
Decide when we start talking and all that stuff.
Excellent. Excellent. So welcome everyone. I think what we'll do is try and leave the questions in the comment box or in the chat box, and then
Yeah.
I can read out the questions to Mike and he can answer them as they come in. So if you have a question, feel free to put it in the comment box.
It'll also depend on how many people show up, right? It may actually be easy to just have people just shout out questions, but let's see how that goes.
Yes, that's true too.
I feel like we should be serving milk and cookies or something while we're waiting for people to get into the room.
Hi, good evening to all.
Oh, good evening, Brett. How are you?
Great, ma'am. How about you?
Good, thank you.
Hi, sir. Actually, I'm pursuing my master's in automotive at University of Windsor, and I find interesting your subject because as automotive engineering student, I had some experience with the automotive tire advice because I submitted the term paper regarding the automotive causes and propagation of automotive tires. So I find interesting. So that's why I joined your
You probably know more about tires than I do. That's great.
no, not basically, but I have a little bit of knowledge regarding the tires, but not in the depth that you are working in the technology of making new innovations and that.
One of the interesting things about this is I'm not a tire guy. I'm a silicone guy. And we just accidentally ended up in this area of technology because we were looking around to do some things with the reactions we were exploring to make silicones, tried this reaction, and to be quite honest, I didn't expect it was going to work at all, certainly not as well as it does. So I'm learning a lot. The nice thing about it is it's a really great vehicle for a bad pun, vehicle for me to learn more about the whole tire business. There's a lot of issues that have to be addressed there.
Yes.
And Brett, do you have any questions that you'd like to ask Mike at this time?
Then I just let's see if
Not to put you on the spot.
everyone is like joining the group section. Let's see where it will going. So
Okay. So we do have a question now from Marley, and they asked, you said the current catalyst is too expensive to use.
So do you want me to run my slides, or do you want to do slides, Amy? Doesn't matter.
I'm happy to do the slides. I can pull them up right now.
Could you go to slide 5 then, please? So thanks for that question. It's really an important one because if you're going to be,
Sorry about that.
yeah, that's the one, 5, yeah, thanks. If you want to do any chemistry, engineers, they don't like to do a lot of processes. So we spent a lot of time figuring out how to optimize this process. And I'm very happy with the 100 degrees for 30 minutes. That's in an industrial terms, that's nothing. But the rubber that we're getting is a pretty dirty material. The sidewall is completely different from the tread. It contains, like I said, steel belts and polyester cord and zinc catalysts and other accelerators and carbon black. There are things in there that are affecting the catalyst, which is that boron compound sitting underneath the blue hydrogen. That's a catalyst that's used in the polyethylene business. So it's something you can buy at scale, but we need 10%. 10%, that's really a lot of catalyst, it's expensive. And so therefore, for this technology to move forward, there's sort of 2 strategies. Can you go to the next slide, please, Amy?
Yes.
So one strategy is to just improve the process. And we're in the business of trying to figure out how we can make the process more efficient, and then using the principles of green chemistry. The other thing you do, obviously, is recover the catalyst and reuse it. So we're in the business of looking at that as well. So that part's okay. But those will be longer term challenges to overcome this, because I think it's pretty amazing. You can take an old tire, and literally we took old tires from the side of the road and you can completely dissolve them. But if you can't afford to do it, nobody cares. So in terms of a business view of things, we think the way to go is to start off with much simpler challenges. So as I said in the presentation, dirty steel has to be landfilled right now. So not only are you paying landfill costs, and now it's going in a landfill, but you're losing the potential money, the income that would come from selling that steel. In this case, we can use not 10%, but 0.1% of the catalyst. And we've done three or four cycles with the same reaction solution and had just as clean outcomes. So in other words, we're somewhere from 10% to 0.3% now, 0.03%, I beg your pardon, catalyst. So all of a sudden, this becomes a viable way to begin the process, because we can develop it so that we only have to dissolve the rubber to clean the steel, but not the rest of the rubber. That will give us, we think, if you want to run a business, you've got to have some kind of profit to pay for research. That, we think, will give us a way in which we can start returning some funding into the research to allow us to look in more detail at the trickier things, the more challenging things of recovering the catalyst and reusing it. So that's our strategy now. It's already working, and I think it's commercially viable for that particular piece of the process. What else can we do? Could you also go to, I don't know if I have a slide there. Maybe I don't have a slide for it. Yeah, can you go to slide 15, please? Thanks. So another thing is to say, why should we dissolve the rubber tire? Because somebody spent a lot of money to take the petroleum and to cross-link it to make this really awesome material. And so a secondary strategy, which involves using way less of the catalyst and way less of the other reagents, is to, for example, what's shown in the middle, just do a little bit of chemistry on the surface of those rubber crumbs so that you can now make a brand new rubber with it. In other words, you're making a nice adhesive layer, we would think, but without the necessity to completely dissolve all the rubber. Or you could take the dissolved rubber and use it as a kind of a glue to glue existing rubbers together. So these are strategies that we're trying to develop that will make it easier to get to some kind of a commercial reality. That's a pretty long-winded answer. I don't know if that's helpful.
Okay, and then Marley just followed up with a quick question about, so you're looking at dissolving the tire enough so that the 0.03% of the catalyst is recovered for the first.
No, I didn't explain that very well. So we use a 0.1% catalyst solution, and we can throw in a batch of steel, and then 15 minutes later, we can take the steel out and it's clean. We can remove it magnetically, of course. Then we can filter off the rubber that hasn't reacted and then reuse this catalyst solution again. So we can do that so far 3 or 4 times, and the efficacy of the catalyst is not changing. And the reason we think is because we're just not doing that much chemistry anymore. So the actual number, we don't know the actual number yet, but it's well less than 0.1%. So there's still no recovery, to answer your question better. That's something that we want to do, but that's yet another process. And we're trying to come up with things that don't involve too many new process steps at the beginning till we have our feet on the ground a little bit.
Excellent. Can I just confirm that everyone's able to see the slides that I'm currently sharing?
Yeah, that's a good question. I can see them.
You can see them. Okay, that's good.
Yeah, we can see them.
Okay, good. Okay, does anybody have, and then one more question here on the chat.
Oh, sorry.
I see that question. So the question is, only 10% of the rubber tire can be reused. Wrong. No, that wasn't correct. 10% is how much catalyst we need. And when you do that, it depends what the specific kind of rubber you're using is. For example, the sidewall is different from the tread, but we can recover about 85 to 95% of the rubber in the form of that oil that can be reprocessed into a new rubber. So the yields are pretty good. The worst yields came when we bought crumb rubber from Amazon, for example. And that's because we don't know where it's come from. And so it's very complicated mixtures, and whatever is in there is inhibiting the catalyst. We can get higher yields, but we have to redo the process more than one time, and that makes it even less viable. So the number that you should be keeping in mind is about 90% recovery of the organic materials that you then separate from all of the fillers, and then those can be reused.
Excellent. So Gavin, I think you were trying to speak a minute ago. I'm not sure if you want to reiterate your question.
Sure. Yeah. Sorry about that for butting in earlier. But I was trying to formulate questions and Mike would answer them. And then I'm like, oh no, I got to redo this question. But it was so thank you, by the way. But I was just wondering, I guess, in general, like, because I kind of heard it earlier. So like after you sort of recycle and get the final rubber products, like what has to be done after that for you to reuse it again? Like
Yeah.
as a tire, for example,
Yeah,
like
great.
what can be reused? What?
Okay, that's a really
Okay,
great question. Let me just see if I've got an appropriate slide there. I guess the best slide would be back to slide number 5, please. So the silicon compound that we're using in there is something, and there are several of these that you can get access to. That's made in high quantities by the silicone industry. Like they make too much of it. They don't want it. So they put it into low value applications. So we have a whole variety of these things that we've optimized. When we do the reaction, you end up with, as is shown in the middle structure, just under the word peroxide, you see that there's a sulfur green and a silicon. So that stuff can be cross-linked directly depending on the source of the rubber. But you have to be careful because over time that silicone is going to be released. So if you think about it, when you go and buy a new car, the first thing they do is they kind of polish the tires and make them look nice and shiny. That's using silicone oil. That's great. But they never put it on the tread because all of a sudden you put your foot on the brake and you just slide on the silicone oil. So that's not really very attractive. So if you wanted to reuse these materials in a friction situation, like the case of a tire where you really have to have good grip on the road, then you would want to instead strip off the silicone. So yes, that's another process, but it's a very simple process, and the silicone just phase separates from the organic material. You get two fluids. That silicone can then be sold to the silicone companies, but what's left then is something that has to be oxidized. And the person who spoke third was talking about oxidizing proteins. And in his case, he needed to get specific oxidation. We don't need specific oxidation. Any old dirty oxidation will work. We use iodine, peroxides, things like that are common in the tire industry that would allow you to then directly go back to make a rubber. I think, but we don't know, that you should be able to put this right back into the standard vulcanization process that's currently used and get a good rubber, but we haven't shown that. That's hypothetical at this point. So we can get some direct cross-linking just by throwing in peroxide, or we can strip off the silicon in a step first and then do a variety of oxidative cross-linking processes.
Thank you.
Pleasure.
Well, I can ask a couple of questions and then, oh, Brett, I see you just came off mute.
Yeah. Hi, Professor. I just have one inquiry regarding the methods you are currently using. Like the tire material which are currently using in the industries are like for example, they are using different materials. Like some materials they are making for the soft materials, and for the hard materials for their tires. So this technique that you are using is it capable for the different materials of tires?
Oh, this is a really good question. So what we discovered is that if we use tires or components of tires that are less complicated, we get better results. For example, if you use a bicycle inner tube, which is made of just one kind of rubber, we can get 95% recovery. If we use a tread, which is typically 2 or 3 kinds of precursors thrown in, you'll have styrene butadiene, you'll have other stuff in there. then the yields are between 85 and 90%. If we use the sidewall, it's again 85 to 92%, I think. So and natural rubber will also, that's been vulcanized, will also degrade under these conditions. We have the worst results when we combine all of the rubbers together, and we don't understand whether that's because there's actually dirt that's getting into the system as the mixture is being formed, or whether there's some kind of synergistic attack on the catalyst. But if we're working with sort of one class of rubber, then the problems aren't so bad. So we've done truck tires, car tires, natural rubber tires, EPDM, and butyl rubber for inner tubes, and they all work over 85% yield.
Oh, that's great.
As long as you don't mix them.
Yeah, I guess that's the problem here arises. I guess many of the tire industry which are currently using, they are not using the one individual type of material in their existing tires.
So to answer your question, we made this decision, and I showed this picture of the tire. We made this decision to not work with pure samples. We took tires. Like I went to a truck company and just said, give me an old tire. They were happy to get rid of it because then they didn't have to worry about it. So we did all our work with used truck tires and used car tires. So that way we would understand exactly what the challenges were with the separation. When you go to one of these companies responsible for shredding tires, for example, and reusing them, they normally would take the whole tire and shred it. But in certain circumstances, they will separate it into two components. They will take the sidewall, they will then remove the bead. That's the part that's actually touching the metal because that's got valuable metal inside. And then they will treat the tread separately because they can sell to different markets those three constituents. So that part of separation is already embedded in the recycling industry. And we were working then with those kinds of separations. I'm not talking about first you have to take your rubber and then break it into all the different kinds of constituents. No, not that. It's the sidewall or the tread or the natural rubber or the inner tube, then it's fine. So in other words, we're just using whatever's going to go otherwise to landfill.
Okay, thanks. That helped.
Thank you.
Excellent. Mike, I was wondering if you could comment on what other technologies are out there that might be similar to yours, or what other competitors there might be in the tire recycling field.
Oh, nothing's as good as our technology. Isn't that what we're supposed to say in a pitch like this? I would argue that from a chemical perspective, there is nothing as good as this technology because the people have tried to do this, and you absolutely can break those sulfur-sulfur bonds. But the conditions that are normally required are much more aggressive. They use much more dangerous chemicals than we're using under much more vigorous conditions. So in terms of complete breakdown, this is a huge improvement. I know I'm biased, but I still think it's a huge improvement. But as I said, it's currently too expensive. The other kinds of technologies that people are using involve the pyrolysis that I talked about. So you essentially take the material and you put it into a reactor, you remove all the oxygen, you heat it up. Sometimes you add some compounds that help break up the sulfur a little bit, but there is no effort to break up the sulfur back to starting materials, and all of the other stuff that's in there, like the carbon black and the silica and so on, that just ends up in the new tire, which is great. If you're going from one tire to another tire, that's fine. You can reuse it up to about, as I said, 10 weight% in the new tire. I think the advantage of breaking it down even more is that we can go into tires, but we can go into other applications as well. So if you want to have a complete closed loop on tires, yes, that would be fine, but this gives you other options. I don't think there are really many other options in between. What you find when you look at this space is that people use different words for partial depolymerization, but at the end of the day, it's just high temperature processes that break down some of those sulfur bonds.
Thank you.
And I don't want to say that's not a good technology because anything is better than nothing, but you can tell by the amount of tires that are being recycled in Ontario, and I've forgotten the number, is about 15 million a year in Ontario alone, but they're recycling them into extremely low value products. They are not going by and large back into tires. So even though if that technology exists, it's not really being widely enough practiced to be, anything's better than nothing, but it's not a huge change over nothing actually in terms of the tire business.
Okay. And I guess another question I had for you was, I was looking at this picture on the screen here with kind of the mini cars or the small reaction vial that you have, and wondering how scalable this this method would be.
It's a really great question. And, you know, every time people like me show stuff, they always show these flasks. And no matter how big the flask is, it's not that big if you're thinking about industrial processes. So the way to answer this question is to ask, how would you actually do this if you wanted to scale it up? Would you do it in a batch? Would you throw everything into a giant blender, for lack of a better word, and just stir? Or would you do it in a continuous process where you would have, for example, what's called an extruder? Basically, it's a giant screw. You put everything in on one end and you force it in by twisting it through a narrow channel where you can add heat and other chemistry and have it come out the other side. When this takes 30 minutes, you could just do it that way. So it's our belief, and it's dangerous. I'm starting to sound like a religious person. It's our belief that this will be scalable, right? There are always going to be headaches that are associated, and I give all the kudos to chemical engineers that are involved in taking smaller scale things that chemists do and scaling them up. But I've been involved in lots of processes, both as a consultant and as an academic. And so I know some of the pitfalls. I think this is an eminently scalable process just based on how easy everything is. It starts as these rubber crumbs and you end up with fluids and stuff that you can filter with a coffee filter. So you're helping yourself in a sense by the products are making it easier to work with them. Whereas I would argue when you take the pyrolysis, you start off with crumb and then you end up with this incredibly viscous dough, which is very hard to process. So I think so, but of course that's what we'll have to prove, and that's really what the next stage of the innovation cascade is going to have to involve, is showing that we can optimize the process, including scale up.
Excellent. We have a question here from Gavin, and he says, as for tire recycling, I believe I remember when we buy tires, we have to pay a recycling fee. Do you see that changing if this technology were to become more mainstream?
I don't know if you're asking the question because you like to say $4 a tire when tires cost $250, or whether there's a different reason. I was surprised to learn that when you pay that money, you're not paying it to the government. You're paying it to the manufacturer of the tire. So if you buy a new car from Ford, they count in Ontario as a tire manufacturer in spite of the fact they don't manufacture the tire. So we are all paying fees that the tire manufacturers, which by the way could include Costco because of their barbecue tires, okay? We are paying the manufacturers to recycle the tires. And in Ontario, at least, the mandate is you have to by weight recycle 85% of the weight of the virgin materials. And the understanding is you drive 100,000 kilometers, you lose about 15% by weight, which means 100% has to be recycled. So let me try and answer this question. If it turns out we can use this material and not have to put stuff into a landfill, that would be a good thing. So one way to then do it is reduce the cost of the recycling fee that is paid. That's one thing you could do. Or, and I hate to say this, or use it as a tax to help other people do innovations for recycling so that more and more things become part of the circular economy. So I guess the question is, at the early stages, if our stuff costs the same amount as not landfilling and so on, then it's a net neutral. But it's just like solar energy or wind energy. It used to be way more expensive, and now it's cheaper than burning gas. So that's really the transition that we would like to make. So I see that there are different visions for this that are going to depend a lot on how the chemistry evolves and the technology evolves, but also the jurisdiction and the regulatory environment that you're in. And I don't think there's a simple answer to that. I would like it to be a way to have our cake and eat it too, that we would be able to have slightly smaller fees and be able to redirect more of this stuff out of landfills. And don't forget, when tires are reused, they're reused for things like making athletic fields, like our sports fields at our universities. But that's a one-time thing, right? Then the second time they're dug up and thrown in the landfill. Well, that's great, but that's, once is better than none at all, but we want to do it every time. And so I think we need to find ways to be able to do that. And that second use, you're not paying any tax on. The athletics field companies aren't paying a recycling tax. So that's a very long answer that probably could have been much shorter. Sorry about that.
Oh, that's a good answer.
Thank you.
And Gavin, I actually skipped over the first part of your question, so I'll just ask it now. It's he wants to know, just to further understand, would you separate the sidewall of the tire from the tread as part of your process?
So what we found is that we got slightly better results when we did that. That's the kind of question that you would answer at scale up. In other words, does the cost of actually undergoing a separation, an additional separation step to break sidewall away from tread, is that justified in the outcome in the improved performance in the reaction? And I guess I don't know the answer to that at this point. What I do know is that there is sometimes a benefit to doing that anyway, because the steel is only in the tread, right? So, and farmers, for example, are quite happy to take the sidewall and use them to cover silage and so on. So there are justifications for doing so. But to explicitly answer that question, we don't know exactly at scale what the penalty will be to have a mixed feed rather than a simple feed. That's something we'd have to look at.
Okay, Kirill here has an interesting question. Does grinding the size of the tire is proportional to the amount of catalyst required if you minimize the volume comparable to the surface area?
That's a really great question. And so we have also done this reaction where we just take literally a chunk, like a 3 or a 5 centimeter by 5 centimeter chunk of tire, and throw it in. And the chemistry works surprisingly well. It just takes forever. Right? So in other words, this is a rate that is affected by the surface area of the crumb that you're exposing to the chemistry. Because it's not like a solution where everything's in solution. You're starting off with a dispersion of chunks of rubber. So the smaller the chunks of rubber, the faster is the process. However, if you want really, really fine particulate of rubber, now you might be using cryogenic grinding, and that costs a lot of money too. So then that's not justified. It's smarter. So if the question is, what is the optimal crumb size that optimizes the cost of the grinding versus the efficiency of the process, that's another issue that we have to address as we go into the scale-up phase of this. But it's not that it doesn't work on bulk materials. It's so much slower. And you can imagine if you stir around 5 centimeter chunks of rubber, stirring them around becomes complicated, and it's just a very, very slow erosion of the material.
Excellent. Yeah, good question. A question from Mark here is, how efficient is the bond breaking? Is the end product, to all intents and purposes, close to original vulcanized rubber?
Okay, that's a really great question. And I was promised by a tire company that I will not name samples of virgin rubber that were explicit. In other words, they had studied them like crazy. They knew exactly what was in there, which would have allowed us to answer this question properly. But they then refused, once our paper was published, they refused to send us the samples. I don't know why. Maybe they're doing something on their own, or maybe they don't like me. I don't know why. Anyway, they said yes, then they wouldn't do it. So that's what we will have to do to try and get the answer to your question. In other words, if you put in styrene butadiene, do you get back exactly the same molecular weight styrene butadiene at the end of the process? It's a super question. We don't know. One of the other things that I think also is relevant to your question is that, and is also relevant for the efficiency of the process, there are some sulfur bonds we want to get rid of. Those are the ones that are closest to the carbon, that's closest to the rubber precursor you're putting in. All the rest of the sulfur, we're using the silicon chemistry to chop it up down into individual sulfur atoms. Well, that's wasting a lot of chemistry. That sort of is it shouldn't be necessary, but guess what? At the moment, we're not able to discriminate between those different kinds of sulfur bonds. So that's something else that we're trying to do, and that is kind of more of an insert sort of heavy duty research with all kinds of fancy schmancy techniques to try and look at. But I think that's beyond the sphere of what we're trying to do on the commercial side at the moment. If we could do that, if we could make it more selective for different kinds of sulfur-sulfur bonds, that would be fantastic, but we're not there yet.
Excellent. I see we have a few new members who joined the breakout room here. So we were just saying earlier, feel free to either post your question in the chat box, or alternatively, you can come off mute because there's not too many people in the room. So don't be shy if you have any questions. One question that I had, Mike, was who do you think would adopt this technology? Like, how do you think that it would become used in the future? And are the techniques, do the techniques themselves, would they require somebody who's very specialized in chemistry or engineering to be able to perform the recycling of the rubber?
Okay, so those are two great questions. Let me answer the second one first. My undergraduates are doing this chemistry. So the answer is you don't need people with lots of skills, because just by definition, undergraduates haven't developed them yet. So this is not hard chemistry. This is really easy chemistry. Having said that, we use toluene, which is a perfectly acceptable solvent. If you look at solvents, it's one of the greener solvents, but we're not consuming it. We're just using it as a vehicle. But that it can burn, right? So you have to worry about that. Hydrogen can be produced as a byproduct in some of the reactions. You have to worry about that too, because it can burn. But these are not insurmountable problems. That's fairly straightforward, I think, to manage. Put it this way: silicone companies and other companies are people that are in the polymer business are doing much more difficult chemistry than this. So that shouldn't be an impediment to this technology. But the first question is really great. Who's going to do this? So do I think that just, Bridgestone, to pick a name out of a hat, is going to take this technology and put it into their tires? No, I don't. Why not? Because they have a huge liability problem. Anybody who remembers the days of Firestone 500s where they had these tires that would blow up when they got a little bit hot, knows that you are now going to be paying lots of money in lawsuits. So it will be a long time before these kinds of technologies, in my opinion, will be developed directly to be reused as tires. I think the liability will be an impediment. So I don't see Goodyear as being the company that's going to do this, for example. I could be wrong. I mean, it's not that we're not going to try and solicit support from them. I think it's going to be, at least in Canada, it's going to be run by jurisdictions. So the Ontario government has got very strict recycling, but at the end of the day, it recycles things once and then they go to much, much lower value materials. I think that is going to drive it. It won't be the Ontario government creating a company. It will be the Ontario government saying to a company, if you can now divert X% from what would be landfill or single second use rubber into something that will go such much more, we will give you a tax break or something, or working with the people that are in the shredding business. They already have all this stuff to deal with. They are the perfect people to say, oh, we could take 10% of our stream tomorrow and upscale it to a value that's higher, not for the tire business necessarily, but for all kinds of other rubber commodities. We use lots and lots of rubber commodities in automobiles as well that don't have the same liability issues. So my sense is it won't be a tire company. It could easily be an automotive company because they are in Ontario, they are manufacturers of tires. But it will also be people that are in the rubber processing business because they're the ones who already know what can be done. And I think an incremental change could give some of their material higher value down the road. So I think it'll be rubber people or people who are now selling tires even if they don't make them.
Thanks.
And I need to clarify, the Ontario government is not going to mandate this. They're not going to give tax breaks. What they're going to do is provide this environment that already exists that says, we would rather do this recycling now because it's going to pay us back as citizens later, and it shouldn't be too expensive for the taxpayer, right? There's this balance because throwing them in the ground I had people who have called me from Texas. I have 1 million tires on my back 40. Would you like to come and get them? Okay, that's the regulatory environment that they are in, which is no environment whatsoever. That used to be Ontario. You'll remember Hagersville, right? Not far from Hamilton, the Hagersville fire, 17 days. That's what happens if you don't take care of them. But the other part is, it's a ridiculous resource to just throw on the ground and hope something good is going to happen from it. So I think the regulatory environment is to prevent those fires from happening, but maybe we can use that same regulatory environment to get higher value out of these materials.
Great. Any other questions from anybody in the room? Oh, sorry, Simranjit, I see you have your hand up.
No worries at all. I just came in a bit late because I was in another breakout room. But thank you very much, Dr. Brook, for the presentation. I'm also a student at McMaster University, so it's great to see some of our institutions' work being presented here. Just so I better understand how, I guess, this all functions. To my understanding, these disulfide bonds exist in essentially all rubber products, and the goal is to figure out a way that they can be more easily broken so we can reuse these products and prevent them from potentially contaminating the environment or being part of dangerous fires. Is that correct understanding?
Yeah. So there are lots of technologies to make rubber out of oil, essentially. And so for example, I do a lot of work in silicone chemistry. And in that case, you never use sulfur to make rubber. There's a lot of other chemistry that's being used. But that vulcanization, that's a word that most of us have heard before. It works extremely well for some very large volume applications, and tires are the classic example, but tires, conveyor belts, all that kind of stuff. So there is a lot of that stuff that's available, that's on the planet, that's being underutilized after its first use. And so what this is really about is trying to break, in the perfect world, just enough of those sulfur-sulfur bonds that we no longer have a rubber, we now have a fluid. Because once we have a fluid, you can pump a fluid, you can pour it in, you can change the shape of your object and make a new material. And so what this is really about is getting back the material in a form that is extremely easy to recross-link into something else.
Okay.
And the way to do that is you can do that two ways. You can go after the carbon chemistry, but that means basically burning it, which is what they do in cement kilns. They use the rubber tires as fuel, but that's a second use. And now it's not sitting on somebody's back 40, but it's better than a barrel of oil because it's been used once. But the idea is to go back to get some kind of a fluid that you can turn into other useful products that in turn could be recycled over and over again. And only when the value of the stuff is so low, maybe you've used it 10 times or 20 times. Okay, now it's just too dirty. We just can't do anything more with it. Now we'll burn it, right? But in the interim, we've taken use of the same carbon atoms and for many applications.
So as of now, what is like the state of the science? What is our capacity to selectively break down an appropriate number of these linkages so the product that is made can be reused, and how accurately can we do that?
Okay, so there are some technologies, they're fairly dated now, that allow you to go in and chew up the sulfur-sulfur bonds, but they're very high energy applications, or they use extremely vigorous / dangerous chemicals to do it. So they are not viable. And I guess when I say not viable is nobody that I'm aware of on the planet is actually using them. They have not found any commercial place as far as I know. Okay. However, the alternative was briefly mentioned in my presentation. You can cook these things up in the absence of oxygen, and that will already break some of the sulfur-sulfur bonds down. And so instead of having a hard rubber like you would have in a tire, you have kind of a soft rubber. It's a dough. It would be more like a rubber ball or something like that. But it's not as highly cross-linked. You can compress it. You can mold it into new shapes. And that's being used already in some new tires. You can use it up to 10% of that in new tires. And by breaking just a few of the bonds and all the other materials that are found in the tire, like carbon black and silica fillers, the catalysts you use, they also just There's no remediation going on. You're just breaking it down so it's a bit more processable and putting it back into the tire. If they could do that and use 100% of the tire and make a new tire out of it, we'd be out of business, right? That our technology wouldn't have enough viability, in my opinion, for us to go forward. I think it's aesthetically interesting to do it, but you can't, because you can't get the properties out of that material when you try and do it a second time. Where when you go all the way back to fluids, then you have the chance to go in and decide how many crosslinks you really want. So it gives you a higher value material, but you've had to pay the money to get to a higher value material.
I assume the complexity of deciding, creating enzymes and proteins it's just probably not there yet, I imagine. Selectively either creating or using, I guess, existing proteins from biological, I guess, origins to selectively break down the disulfide bonds in an appropriate way.
So I thought that was a really cool presentation that we heard, the one that was just after mine, where he's building these disulfide linkages selectively in proteins. And the best way for me to answer your question is that if you put a rubber tire in my backyard today and come back 400 years from now, it's still going to be sitting there. And if you put it in Florida, it'll still be sitting there, even though you've got all the heat and the organisms. And if you throw it in the ocean, it'll still be sitting there. So all of the enzymes that are floating around in nature that are designed so well to break stuff down do not work well on these sulfur-sulfur bonds. And the reason, I think, why are they able to do it on enzymes? The enzyme has only a single sulfur-sulfur bond. That's number one. And the enzyme is surrounded by a bunch of stuff that dissolves in water, or at least swells in water. So the enzyme can go in, find that sulfur-sulfur linkage, chop it in two, and then reuse it any way it wants. And the chemistry, glutathione couples, and there are a variety of other chemistries that biology uses to do these oxidation reductions. It doesn't work with rubber because those enzymes can't get into the rubber to actually do that kind of chemistry. And they're not designed to take sulfur-sulfur bonds apart, just a single disulfide from cysteines typically. So that would be great. If we could ferment these things and get them to break down into smaller materials by only breaking the sulfur, that'd be awesome. But I just don't think that's likely to happen. It's the same kind of problem that we have with water bottles. You can grind them up and now you get microplastics, but they still don't degrade very well.
Thank you very much, Dr. Burke.
It's a pleasure. Thank you for your questions.
Certainly.
We do have another question on the chat here from Kirill. It's instead of breaking up the tire fully, can you use this technology for retreading the tires by breaking up a specific layer and putting new tread after cleaning up the damaged area?
Can I ask you to go to slide, which one is it now? Just a moment, please. Unfortunately, my face is sitting on top of the slide. So there we are. It's 15, please. This is really a great question. So there are, of course, companies right now that will retread your tire. But you have to have enough of your tread left for this new tire, this new rubber to grab onto it. I wonder if I asked the 100 people that were on the call earlier whether any of them have ever had their tires retreaded, and the answer is probably no, because that technology comes with it liability, because it's not just the integrity of the new rubber that you're making on the outer surface, but it's the integrity of the lamination between the new rubber and the existing old rubber. So do I think it could work? Maybe. Do I think it's ever going to happen? Probably not. But the reason I asked to show this slide, it comes back to something I think I mentioned earlier, is that there's two ways to think about this. In the middle is an idea where we would take the crumb surface and just make the chemistry happen on the surface of the crumb without degrading all of the rubbers. So we'd need way less chemistry. And now we should be able to take that activated material, and either the red lines there, which is this chemistry that we're doing, will be enough to glue them together. Or you don't care. You now just take these rubber crumbs that are pre-activated, ready to bind, and throw them into the yellow matrix shown on the right. And so what we're talking about here is now just activating it so that on a small scale, high surface area application, the existing rubber can be now dissolved away. So in other words, you're going to take the contaminants and all the other junk that's on the surface of the crumb, clean it up by etching it away, then taking that activated surface and putting it into new vulcanization. This is a way where I think we could be using way less of our chemistry. And maybe you could put it into an application like retreading, but I don't think even if it was to work, people would adopt it just because of the liability issues that I brought up earlier. I think much better would be to put it into a different application where you're not quite as worried about that.
Thank you. That sounds.
Thank you.
Thank you very much, Dr. Brooks. I think I'll head to another breakout room.
Very much for coming up. I very much appreciate it.
Thank you very much for your question answers. Have a great day.
Thanks for joining.
Thanks for joining.
Okay.
So, what's the normal time? I wasn't paying attention. What's the normal time frame for this competition or for these question and answers?
So this period now, we have until 6 p.m. That's what it's booked, but it's flexible. So if there's not really any more questions coming in, then we can sort of.
I'm going to hang out till 6. That's not. I just couldn't remember. And then we go back into the main room, right?
I think we can, but I think it's over after this.
It's over.
Yeah. The launch event has ended. Yeah.
No, that's fine. I know I should know all these details, but I didn't pay enough attention.
Oh, I should know these details. Excellent. Well, I mean, I have a few more questions that I think probably overlap with some of the questions and answers you've already given, but I mean, I can.
Sure.
Just for the sake of interest. One question I had was what barriers do you think there are going to be for adoption of this method or this technology?
Do you mean acceptance of the final material itself, or do you mean
more so
coming in and investing to say we think this has legs?
Yes, I think barriers towards commercialization of this technology.
I think so. You know, part of this is a competition where you have to write a business plan. We don't know what the real cost of this catalyst is at scale. So part of the problem is I know this catalyst costs a lot of money, but if we cannot get as little people, at least I haven't been able so far to get a real cost per ton of this catalyst from the polyolefin business, and that's going to be really important. So somebody who's in the game will be able to get that. I mean, if a tire company phoned the manufacturer and said we want a ton, they'd get a hard price. So part of the challenge will be convincing someone to sort of do some of the costing out and getting realistic costs. Most of them are pretty simple, but the catalyst is one that's a little bit more complicated. And the other thing I think that associated with that is they're going to want to know, let's suppose you have to use 10%. Well, what the hell do we do with that? That's just a new contaminant, right? So wait a minute, now how much are we going to have to pay to landfill this dirty black liquor that's got your catalyst in there? And the answer is we can't do that. We have to be able to recover it. So I think there are going to be some early stage requirements. These are going to be, gated decisions, right? Like milestones. If we don't know that we can actually take however much catalyst we use in this process and recover 99.99% in a form that is safely disposed of, or even better, can be reused, we're just creating a different environmental problem. So that's one of the things that's going to have to be dealt with. The cost of the catalyst itself has to be dealt with. Much of the rest of this, however, is a no-brainer. I mean, if you want rubber, there's no shortage of feedstock. You can have as much as you want. That's very attractive. There's no problem with that. The existing technologies are there to capture how many of the tires have been collected, to find out how many of them have gone to the shredding. That's all part of it. The Ontario system right now, they know where all the tires are going. There's very good data for that. So it makes it pretty easy to work with these people that are already in the recycling business, because they will know where the price points are, where the profit margins on. I mean, they also could be people that would be interested in this technology because they would directly benefit. But they will be the ones that will say, to be able to answer the question, how clean can I make the steel? How clean do I need the steel to be? And these are all the commercial decisions. If we only have to get off 5% of the rubber rather than 50% of the rubber to sell to the steel company, that's important. Well, I don't know any of those details at the moment. So I think for adoption, somebody has to go in and do pricing, like for any business plan. Somebody has to then decide what is the market. Right now, the tires are being used in very low value applications by and large. How much would people pay to have clean starting material compared to virgin oil that's coming from petroleum? That's another question that will have to be asked. So I think a lot of this is not really a chemical issue aside from the cost and the recovery of the catalyst. It's really about what the market will bear.
Excellent. Thank you, Mike. I don't actually know if you've seen some of the chat, but there were a few thank yous that came in. So just thank you very much for your answers, and they really appreciate your thoughtful answers. So yeah.
Well, I appreciate people's interest. This is we all have stuff to do. So the fact that people are taking the time to sort of listen to this and the other question and answer sessions and the presentations is great. So I'm very grateful for people's time.
Yeah, it'll be exciting to see in January how many applications or submissions we get for the first stage.
Yeah.
Yeah. So
help me out here. If in fact somebody decides that they want to do this tire project, then I presume what that really means is that I will be involved as the technical advisor to help them with some of this stuff.
Yes. Yep. So if anybody has questions about the technology or want to bounce ideas off of you, they can contact you if that's okay with you. And they can also go through me because I might be able to help answer some of the questions as well. But yeah, between the two of us, we can definitely try and help to have discussions.
I see. So this is a multi-layer competition. So this is my technology against everybody else's technology. It's McMaster against all the other universities. I presume that's part of it, right? In other words, that's by design. It's about trying to get the best out of what we have in these 6 universities.
Yeah, so I don't think the technologies themselves are kind of competing against each other, but it's more so the students or participants who sign up for each of the technologies are competing against each other for the best business plan and ultimately pitch. And then one winner from each of the technologies will be chosen at the end.
Good. And do I get to buy the business plan from them? Is that how it's going to work when they have one on my technology?
So I think after the competition, there's definitely an opportunity if you're interested and the participants are interested to kind of continue the discussions further. So
one of the things I really like about this whole day is that it's very hard for people who aren't technical to figure out what the elements of the technology are and what are the hard things and easy things to do. Whereas for me, that's trivial. What I have trouble with is how do I get people to get interested in this? And what is the plan? And how much money do we need to get from here to stage A to get to stage B to making $1 gazillion so I can retire? And I don't know what that pathway really looks like. So it's nice because it puts people together with these different skill sets.
Exactly. And Brett, Krill, and Ellie, have either any of you participated in something similar or completed a business plan or pitch competition before?
Actually, from my side, technically no. That's why I'm a little nervous in this. So I have that question regarding this plan, like what after this, like after this seminar, so what's the next step that we have to take to participate in this project? Or
Good question. Yeah. So basically, there's a few different steps, and along the way, it's each of your submissions will be judged, and only a certain group of people will move forward in each kind of phase of the competition. So the first stage, which the deadline Lisa had mentioned was January 11th. I'm just going to, yes, January 11th is basically you submit an abstract, and that's all of this information can be found right on the Proteus website. So let me actually send the links just so you have it.
That's a good idea.
And that's where you can see kind of the different stages. So there's 3 more stages. But the first is an abstract. It's not too long. I think it's 250 words. And that's also your kind of application to be part of the competition. And then after that stage, you then move forward to building your business plan. So this is due February 11th, so only a month after you submit your abstract. And along the way for the business plan and pitch, there will be workshops. So you're not completely kind of alone in building up your business plan and workshop. The Proteus organizers usually will host an event where you can learn, you know, what should I put in this business plan and what are the important components and things like that. So it's kind of a good learning opportunity as well for you to practice doing these things, business plan and pitch, which is really helpful, especially if you're interested in commercialization of research in general, or even moving into kind of more of a business position later on in your career.
Yes, definitely. Thanks. That would help.
And I see, Tian, you've recently joined the room. I just want to make sure that we have time for you to ask any questions to Dr. Brook if you have any.
Like in your introduction, you mentioned about the expense is a little bit high for the side. I mean,
The catalyst.
yeah, the catalyst.
Yeah.
So how does it compare to like they just make a new tire?
So that's a really great question. So don't forget, when they're making a tire, they're building sulfur-sulfur bonds, and we're trying to break them apart. So it's a different catalyst that's being used, and their catalyst is way cheaper, way cheaper. So that's part of the challenge, is that what we're doing involves a much more expensive catalyst. So the difference is, if we do it right, we can recover the catalyst. When you make the tire, whatever catalyst they use, it's in the tire, right? But our process, because we're going from rubber to fluid, we can recapture, we think, we can recapture and reuse the catalyst. That's certainly our hope. So that at the beginning, per kilogram, it's going to be much more expensive. But the hope is that when you actually look at it per kilogram of product, after you've reused the catalyst, it won't be all that much different. But that's my aspiration. At the moment, we're not doing that. We're not recovering it at this stage. That's something we have to work on and optimize in the next stage of the development.
So which means we need a great amount of input.
At the moment, yeah. So if you want to take it, so the trickiest job is to take a tire, really an existing automobile tire, grind it up, and if you want all of that material, or at least our yields are over 90%, let's call it 90%, to make this fluid from the tire, you need a lot of catalyst. Like I said, it's 10%. That's a lot. Catalyst should be operating at 1% or 0.1%. So it's too much catalyst, and it's a consequence, I think, of the fact that there's a lot of stuff in the tire, including the catalyst they use to make it, that is inhibiting our catalyst. So that's one of the things we have to do to improve this technology.
Thank you.
Thank you.
Excellent. Well, we're getting close to 6 o'clock.
It is 6 o'clock. We made it.
Yes. Okay, good question, Brett. What I can do is, if you're interested specifically in the McMaster technology, you can contact me. I'll just send my email through the chat here. I'm not very good at multitasking. And I'd be happy to try and answer your questions, or I can also put you in touch with Dr. Brook.
Yeah.
And if you have any questions about the Proteus event in general, you can also contact me and I can put you in touch with Jordan and Lisa. Or I think there's a Proteus email on the website as well. But yeah, however you want to do it, you can contact me, and that works as well.
Good.
Excellent. Well, thank you so much, Mike, for all your time today.
Oh, it's a pleasure. Thanks to everybody who showed up and then hung around. I really appreciate your enthusiasm and interest. And Amy, thanks for It's our kind of for running the show. It's very nice to have somebody who can take care of the details and not have it to be me. Because as you say, multitasking is not always trivial. So.
No. Yeah, it's a skill, that's for sure. Okay.
Super.
Well, thank you
Thanks
so much.
again. I really appreciate everyone's interest.
Excellent.
Maybe we'll talk again.
Hopefully see you guys at the next stage.
Excuse me, I have another question.
Oh, sure.
Like, if we want to like rebuy the tire for recycling, and how do we know it is a common tire or the tire that can be recycled?
Oh, that's a great question. So this technology works so far on every tire we've tried. So what we've tried are natural rubber, truck tires, car tires, bicycle inner tubes, EPDM. It works on all of these tires. So the technology, as far as we know, as long as the tire was made using sulfur as the curing agent, this technology works. Now, it doesn't work equally well on all of the materials. So we found somewhat better results if we have only the sidewall or only the tread. But the yields are always between 85 and 95%. So it's not that big a difference. So every tire should be susceptible to this degradation. Is that your question? I'm not sure. I want to make sure that's your question.
I mean, like if we produce some tire and sell them, and we know it can be recycled.
Yes.
And how do we identify like if the tire was sold by another company or the tire we sold?
Oh, I see. So this is kind of a strategy for the actual sales where you basically would say, we're selling a tire that can be degraded at the end of life. The problem is at the moment, everybody's tire could be degraded using this technology, right? So that's not, it's not like, it's important. I understand what you're saying. It's like, Monsanto makes these seeds that need Roundup. So when you buy the Monsanto seeds, they're going to be resistant to certain weeds, but you have to sell your seeds to Monsanto at the end. So it's a very integrated system. In this case, our technology at the moment works with every tire we've tried. So there's no ability to differentiate between the different kinds of rubber from the different manufacturers.
Okay, I think. Thank you.
Thank you. Great. Any others? Okay, good. Well, thank you again. It was nice to meet you, and maybe I'll meet some of you if you actually go through to write the business plan. I can be your technical advisor. Thanks a lot.
Thank you so much, Mike.
Bye
Have a
for
good
now.
evening, everyone.
You too. Yes, everyone, please have a good evening. Bye.
Bye.